You are floating in the dark beyond every planet, and in the headphones, there is a sound so thin it almost feels imagined. Voyager 1 is the one hearing it. This tiny machine, launched before many grandparents had gray hair, is now so far from Earth that a simple radio reply takes nearly 2 days to make the round trip, and what it is picking up may be telling us that deep space is not what we thought it was. If you like stories that turn old space facts into fresh clues, stay with me and subscribe, because this channel is where quiet signals become bigger maps of the universe. Out there, sunlight is weak. The sun is just another bright star, and the old idea of the solar system has already fallen behind. Voyager 1 is not skimming past Jupiter anymore. It is not giving us postcard pictures of Saturn. It is moving through interstellar space, the region between the stars, and it is doing it with hardware that belongs in a museum. That is part of what makes this story feel so strange. We are used to imagining future discoveries arriving from shiny new machines, all clean edges and fresh batteries. Instead, one of the biggest surprises in deep space science is coming from a craft launched on September 5, 1977, a machine that still works because engineers keep nursing it forward one careful choice at a time. And the surprise is not some giant object flashing past its cameras. It is not a neat movie moment at all. It is a faint, persistent signal in a place most of us were taught to picture as empty, calm, and almost featureless. The deeper scientists listened, the less that picture held together. To see why this matters, we need to step back. Most people think that once a spacecraft leaves the sun's bubble, it enters a simpler place, a cold and mostly empty stretch where not much changes and almost nothing happens. Deep space, in that picture, is just distance. Voyager 1 did not begin as an interstellar explorer. It began as a fast, daring visitor to the giant planets, a machine built by NASA's Jet Propulsion Laboratory to rush outward and take advantage of a rare lineup of worlds. It launched after Voyager 2, but on a quicker path, and by December 15, 1977, it had already overtaken its twin. Even in that first year, it was moving with the kind of purpose that makes space history feel alive. At Jupiter in 1979, it found a faint ring and 2 new moons, Thebe and Metis. At Saturn in 1980, it found 5 new moons and a new ring, and it gave the world close looks at Titan, the big moon wrapped in thick haze. Those discoveries were loud, visual, and easy to love. They fit the way we think discovery is supposed to feel. Then Voyager 1 did something less flashy, and in the long run, maybe even more important. It turned away from the easy center of attention and kept going. NASA formally began the Voyager interstellar mission on January 1, 1990, extending the goal from planet visits to the edge of the sun's reach and beyond. From that point on, the story became slower, stranger, and much harder to picture. It helps to know what boundary Voyager 1 was heading toward. The sun does not just shine, it also blows out a constant stream of charged particles called the solar wind. That wind inflates a vast magnetic bubble around the solar system, called the heliosphere. The outer edge of that bubble, where the influence of interstellar space starts to win, is called the heliopause. For years, that boundary sounded almost simple in the public imagination. Inside the bubble is us. Outside the bubble is everything else. Cross the line, and the old solar story ends. If that were true in a clean, simple way, then Voyager 1's later years would be important, but maybe not dramatic. By August 25, 2012, NASA says Voyager 1 became the first human-made object to exit the heliosphere and begin measuring the interstellar environment. That phrase sounds calm, measuring the interstellar environment, but hidden inside it is a huge shift. For the first time, a machine built by human hands was directly sampling the stuff between the stars instead of guessing at it from far away. And what was Voyager carrying into that darkness? Not just memories of Jupiter and Saturn, it still had working instruments. The ones most important to this story were the magnetometer, which measures magnetic fields, and the plasma waves subsystem, which listens for vibrations in plasma, a gas whose particles carry electric charge. On Voyager 1, that system included 2 long antennas that stretched like thin metal ears behind the spacecraft. That detail matters because the space beyond the heliopause was never going to be seen the way a mountain or a moon is seen. It had to be heard through numbers. It had to be felt through shifts in density, charge, and magnetic direction. This was not a camera story anymore. It was a listening story. That is one reason so many people overlook Voyager 1 now. The mission moved from pictures to patterns. The drama moved from bright rings and storm clouds to tiny changes in data. If you are scrolling fast, it is easy to think the probe is just drifting through black emptiness and sending home the same old whisper year after year. Even the scale works against our instincts. As of August 21st, 2024, NASA reported Voyager 1 at 164.7 astronomical units from Earth. 1 astronomical unit is the average distance between Earth and the Sun. Put that another way, Voyager 1 was more than 15 billion miles, or 24 billion kilometers from home. Numbers like that are so large they can stop feeling real. So people shrink the story down into one easy belief. Past the heliopause, space must be mostly uniform. The sun is behind you. The planets are behind you. The messy part is over. Whatever remains out there should be thin, quiet, and straightforward, like walking out of a noisy house into a still winter field. NASA's own milestone language almost tempts us to think that way. First spacecraft to cross. First spacecraft to enter. First spacecraft to measure. Those are clean historical marks. They sound like doors swinging open onto stable ground. By the end of this setup, it is easy to believe that Voyager 1 entered a simpler world than the one it left. But that picture is about to change. The farther scientists pushed past the idea of empty space, the less empty it looked, and the less simple it behaved. Write the moment your old picture cracks in the comments, because that exact point of surprise helps shape the next story we build here. What we have just taken for granted turns out to be a small part of a much larger story. The crossing of the heliopause was not the end of the mystery. It was the moment the real listening began. The first shock came almost immediately after the crossing. If scientists expected deep space to settle into a thin, quiet background, Voyager 1 gave them something else. In November 2012, just 3 months after entering interstellar space, its plasma wave instrument picked up a kind of whistle, a vibration that revealed the density of plasma around it. 6 months later, another whistle arrived, louder and higher in pitch. Here is the surprise pattern in plain language. Scientists expected the medium outside the sun's bubble to be thin and fairly steady. Voyager 1 found plasma densities much higher than they had inside the boundary, with measurements indicating a jump of about 40 times. It was like stepping through a door expecting open fog and finding cold rain pressing much harder against your skin. That alone was enough to change the story. The heliopause was not just a line on a diagram, it was a real border between different conditions, and the space just outside it had more structure than many people imagined. The neat textbook picture started to wobble. But those whistles had a limit. They appeared only at irregular times, about once a year, according to the later work that studied them. That meant scientists could only map the density in scattered snapshots. Imagine trying to understand the ocean by hearing one wave every few months. You would know the sea is there, but not how it is moving around you. That problem led to one of the most important names in this story. Stella Oker, then a PhD student at Cornell University, went looking through Voyager 1 data for something weaker but steadier. Her 2021 study in Nature Astronomy reported a class of very weak, narrowband plasma wave emission that persisted from 2017 onward. In simple words, Voyager 1 was not just hearing rare whistles anymore. It was hearing a faint, nearly continuous hum. Again, the surprise comes in 3 beats. Scientists expected long, quiet gaps between the bigger, shock-triggered events. Instead, they found a thin, single-tone signal that kept going over years. It was like expecting a dark room to go silent after thunder, then realizing an air vent has been singing softly the whole time. Oker described it as virtually a single tone. Jim Cordes, a Cornell space physicist and co-author, helped frame what that meant. People like to talk about the quiet interstellar medium, he said, but lots of places are not quiet at all. The phrase interstellar medium simply means the material between the stars, a spread-out mix of particles, fields, and radiation, and Voyager 1 was revealing that this nearby region had texture. The numbers made that texture harder to ignore. Based on the signal Oker and her team studied, the electron density around Voyager 1 began rising in 2013 and reached its then current levels around mid-2015, a roughly 40-fold increase. Through the dataset they analyzed, which ran into early 2020, the spacecraft stayed in a similar density range with fluctuations. Deep space was not flattening into sameness, it was changing over time. Think about that from a human scale. We like crossings to behave like switches. You step over a doorstep and you are inside. You step back and you are outside. Voyager 1 crossed a famous boundary, but what it met beyond that boundary was more like weather than architecture. Not a single clean room, but a region with currents, layers, and leftover influence. That idea was reinforced by another puzzle, one involving magnetic fields. If Voyager 1 had truly stepped into a pristine, untouched part of interstellar space, many expected the local magnetic field to line up with what other observations suggested was the true direction outside the heliosphere. But it did not. The field direction observed by Voyager 1 was more than 40 degrees off. Here is the three-beat turn again. Scientists expected a compass-like agreement right after the crossing. Voyager 1 found a field bent away from that expected direction. It was like sailing out of a harbor, looking at the stars for north, and discovering your needle still tugged toward the shoreline behind you. A study highlighted by JPL and published in the astrophysical journal Letters took that mystery seriously. Nathan Schwadron of the University of New Hampshire and colleagues reanalyzed Voyager 1 magnetic field data and argued that the field had been slowly turning ever since the spacecraft crossed into interstellar space. Their idea was not that Voyager had failed to leave the heliosphere, but that the nearby boundary was still shaping the field around it. Schwadron used a great image for this. If the magnetic field is like a rubber band stretched around a beach ball, then that band gets deflected around the heliopause. In other words, the sun's bubble does not stop mattering the instant you leave it. Its wake bends the local conditions just outside the edge. That helped explain why Voyager 1 and another line of evidence did not match at first. Back in 2009, NASA's Interstellar Boundary Explorer, or IBEX, discovered a ribbon of energetic neutral atoms, strange fast particles that traced a broad arc in the sky. Scientists linked the center of that ribbon to the direction of the more pristine interstellar magnetic field. Data from Ulysses and SOHO also pointed that way. So there was the conflict. One set of clues, from IBEX and other spacecraft, suggested one direction. Voyager 1, right there on the scene, appeared to be seeing another. The easy assumption would have been that one of them had to be wrong. The deeper answer was more interesting. Both could be right if Voyager 1 was still in a disturbed zone, a region outside the heliopause but not yet free of the sun's shove. That is a huge emotional shift in the story. The old public version says Voyager 1 crossed a border and entered the unknown. The newer, more honest version says it crossed a border and entered a transition zone whose behavior still carried the memory of home. Even outside the sun's bubble, the sun had not fully let go. And then there is the question hidden inside the title of this video. What exactly is that persistent hum? This is where the mystery stays real. Auker's paper reports the signal and shows why it is useful, but the team also said they were still trying to develop a physical model for how the emission is produced. They suggested it may be generated by thermally or superthermally excited plasma oscillations, which is a technical way of saying the plasma may be vibrating because particles there have the right kind of energy. But that is not the same as a final explanation. This is the moment where a trustworthy story has to slow down. Scientists do not fully agree on every mechanism yet, and they do not fully understand every layer of the local interstellar medium. The signal is real. Its usefulness is real. The map it gives us is real. But the exact process making that faint tone is still being worked out, and that uncertainty is part of the discovery, not a flaw in it. There is one more confusion to clear away because it matters for how this story gets told online. In late 2023 and early 2024, Voyager 1 had a serious engineering problem. NASA reported that the spacecraft was sending a steady radio signal, but the signal did not contain usable data. The source appeared to involve the Flight Data Subsystem, one of the onboard computers responsible for packaging science and engineering information. That was strange, but it was not the deep space mystery itself. It was a spacecraft systems problem. On March 1st, 2024, engineers sent what they called a poke to prompt the computer into trying different sequences. By March 3rd, they saw a changed response, and by March 10th, they had identified it as a memory readout. That story is about keeping an old machine alive. The plasma hum story is about what the machine had already heard in the dark. Keeping those two stories separate lets the real reveal breathe. Voyager 1 is not exciting because it glitched. It is exciting because, even while aging and fragile, it keeps telling us that the nearby interstellar medium is active, structured, and not yet fully explained. The place beyond the planets is not a silent hallway. It is more like the shore of a larger sea. And here is where this stops being about one machine and begins being about us. If the space just beyond our sun's bubble is layered, bent, and quietly humming, then the way we think about our own neighborhood has to change with it. Share this with the one friend who still pictures deep space as blank nothing, because passing this story on gives both of you a better map for the next strange signal. What looked like emptiness now looks like environment. What looked like distance now looks like a place with behavior. And once you accept that, the rest of the future opens in a different way. The first thing that changes is our sense of where we live. Earth does not sit in open space like a marble on a shelf. It sits inside a moving bubble blown by the sun, and that bubble has an edge, a wake, and a relationship with the galaxy around it. Voyager 1 has shown that the neighborhood outside that bubble is not just out there, it is pressing back. That matters even if you never take a physics class again. When you hear weather on Earth, you understand that your house exists inside larger systems. Wind, pressure, heat, clouds. Voyager 1 is doing the same thing for the solar system. It is helping us feel that our cosmic home also has weather-like structure, only the scales are almost too large to hold in the mind. The second change is practical. Future deep space missions cannot assume that outside means simple. If plasma density changes over years, if magnetic fields remain bent near the heliopause, and if weak emissions can reveal hidden structure, then instruments have to be built for patience. The lesson of Voyager 1 is not just go farther, it is listen longer. The third change is emotional. We often tell space history as a parade of heroic firsts, and those firsts matter. But Voyager 1 teaches a quieter kind of courage. It has been traveling since 1977. It stopped taking pictures long ago. It now returns data in tiny, delayed conversations across staggering distance. Yet some of its deepest contributions are arriving at the slowest possible pace, one narrow signal at a time. By August 21, 2024, NASA placed Voyager 1 at 164.7 astronomical units from Earth and moving at 17.0 kilometers per second relative to the Sun. In March 2024, NASA also reminded the public that a radio signal takes 22.5 hours to reach the spacecraft and another 22.5 hours for the reply to return. That means every act of troubleshooting, every check, every correction, lives inside a delay longer than many weekend trips. Bring that down to the kitchen table for a second. Your phone freezes, and you expect a fix in minutes. Voyager 1 stalls, and the engineers spend nearly 2 full days just waiting to learn what one command did. That distance changes the meaning of patience. It also makes every surviving science return feel almost tender. There is also the hard reality of time. NASA's Voyager mission page says that on April 17th, engineers shut off an instrument on Voyager 1 to save power and keep the spacecraft operating. The same page says 2 science instruments remain active nearly 49 years into the mission. So the future of this story is not guaranteed by excitement alone. It is being bought with sacrifice, watt by watt. That gives the unresolved questions more weight. Will the plasma density stay in the same range, or shift again as Voyager 1 moves farther from the heliopause's influence? Will the magnetic field keep turning toward the direction inferred from the ibex ribbon, showing that the spacecraft is entering a less disturbed region? Will scientists pin down the exact mechanism behind the persistent narrowband emission? Those are not abstract questions anymore. They are questions being asked with a machine that is running out of power. This is why real dates and numbers start to matter more near the end of the story. September 5th, 1977 was the launch. August 25th, 2012 was the crossing into interstellar space. March 1st, March 3rd, March 7th, and March 10th of 2024 were key days in decoding the engineering fault. April 17, 2026 marked another power-saving step. These dates form a kind of heartbeat. They remind us that deep space discovery is not one giant leap frozen in history. It is an ongoing chain of exact moments. And if you are wondering what to look for next, the answer is not a giant explosion or a perfect press conference phrase. It is subtle movement. It is whether the density trends hold. It is whether the magnetic field continues to ease toward a more pristine direction. It is whether a faint tone around a few kilohertz, a few thousand cycles per second, keeps whispering that the local interstellar medium has more structure to give up. Researchers and institutions matter here because they keep the story anchored. NASA and JPL continue to operate Voyager. Cornell scientists like Stella Acker and Jim Cordes helped show that the persistent signal can map density across long stretches of space. Work described by JPL around Nathan Schwadron's team helped explain why the magnetic field around Voyager 1 may still be bent by the nearby boundary. This is how the unknown becomes readable, not in one shout, but in many careful passes. So what changes because of the reveal? We stop thinking of the solar system as a sealed room. We start thinking of it as a boat moving through a medium we are only beginning to sense. And we realize that one of the oldest machines we ever sent away from home may still be teaching us how to imagine outside correctly. Something new is going to arrive before the story feels finished. It may be one more shift in density. It may be a cleaner turn in the magnetic field. It may be a better model for the source of that hum. It may simply be another reminder that the most important discoveries are sometimes the ones that barely rise above the noise. The next horizon in this story is not dramatic because it is loud. It is dramatic because it is precise. A tiny spacecraft, older than many of the people talking about it online, is still crossing real distance through a real environment. Each added fraction of an astronomical unit is another step away from the sun's immediate memory, and another chance to hear a truer version of interstellar space. That is why this story leaves me with one image more than any other. Not the golden record, not Saturn's rings, not even the heliopause. I think about a faint, narrow tone traveling through the data, a nearly single note carried across 22.5 hours of radio silence, arriving from more than 164 astronomical units away to tell us that the dark is not dead. Save this story somewhere private and come back to it, because keeping one quiet marker like this helps you notice when the future slips from rumor into fact. Years from now, when another update arrives, you may hear the difference instantly. You may remember that the universe did not announce this lesson with fireworks. It announced it with a whisper. And that whisper says something beautiful. It says the space beyond our maps is still textured. It says our sun's bubble has a shoreline. It says the old machine is still moving. And it says the future will belong, at least in part, to the people patient enough to listen for what should not have been there, but was.